Now let's talk about related rates. Related rates are a lot of fun, but they're also a little bit confusing. Suppose I drop a pebble into a pond, and initially the area of that circle, area, is going to be pi r squared. Now, you can see as time goes on and the circles get bigger that the area is changing. And as a matter of fact, the area is changing with respect to time. So we could do something. What if we took the derivative of this area with respect to time? That would give us a rate of change of the area. And that would be pi times 2r times the derivative of r with respect to t. So basically what we're doing is we're finding how is the area related to how's the change in area related to the change in radius. So for this example, dA dt, it's 2 pi r dr dt. So that's how we're going to do all of our related rates problems. I wish I could tell you there was a simple formula, but there's not. For any related rates problem, you need to make sure you identify all of the given quantities. Just write them out. And then all of the quantities that are to be determined. And make sure you draw a sketch if possible. It doesn't have to be colorful. Then write some sort of equation involving the variables. I'm going to give you a list of equations that you need to memorize and know at the end of the video. Then you're going to need to use a chain rule and do implicit differentiation on both sides. But we're going to do the differentiation with respect to time. After you're done with the step 3, you're just going to go back and solve for what you're looking for. The easiest way to do these is to just do them. Suppose I have a point moving along a graph of a given function, and y is equal to the tangent of x. Find dy dt for the given values. All right, so if I do dy dt, ddt of both sides, this is going to be d dt of tan x. Now let's see what we have. We wind up with dy dt equals. Now the derivative with respect to t of tangent is going to be secant squared x, but we have to take the derivative of the argument, so that's going to be dx dt. Now, I knew that x is negative 3/2, and I also know that dx dt is 2 centimeters per second. Do you see I'm including my units? It's essential you include your units. So I'm looking for dy dt. So this is going to be secant squared. Now my x value is minus pi over 3. And dx dt is 2 centimeters per second. So this becomes secant squared. So this is 2 squared times 2, or 8 centimeters per second. When x is minus pi over 4, I start right here. Okay, I start at the same spot right here. You don't have to redo anything. dy dt is secant squared, but you do have to plug it in, of minus pi over 4 times dx dt, which is 2 centimeters per second. So on parts A, B, C, and D, you don't have to redo the derivative, but you do have to show the plugging in part. So this becomes, say, secant squared of minus pi over 4 is square root of 2. And that's squared times 2, so that's 2 times 2 is 4 centimeters per second. Now finally, when x is 0, dy dt is going to equal secant squared of 0 times 2 centimeters per second. So that's 1 times 2 is 2 centimeters per second. All right, now you give it a go. See if you can do this one. Now, what do you do if you have a spherical balloon? A spherical balloon is a lot of fun, and we do a lot of these. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. So I know dV dt is given by 800 centimeters cubed per minute. How fast is the radius of the balloon increasing? So what are we looking for here? We're looking for how fast the radius is increasing, so we're looking for dr dt. At the instant, the radius is 30 centimeters, so the first r is 30 centimeters, the second r is 60 centimeters. Now we know that the volume of a balloon is 4/3 pi r cubed. So if the volume is 4/3 pi r cubed, what I need to do is take the derivative with respect to t of the entire thing. So this is going to be dv dt, and then it's going to be 4/3 pi. Now the derivative of r cubed is 3r squared times the derivative with respect to r of t. So dv dt is equal to 4 pi r squared dr dt. All right, now we're looking for dr dt. So let me solve this for dr dt. dr dt is equal to dv dt. Whoops, let me undo that. dv dt times 1/4 pi r squared. That's what happens when you get to the bottom of your slate down here. It's kind of hard. Okay, so dv dt is 800 times 1 divided by 4 pi. My r in this case is 30 squared. So I get a dr dt of about 2 divided by 9 pi centimeters per minute. All right. Now, if I want to do it when r is 60, I just have to come back to this point right here. All right. So dr dt is dv dt, which is 800 times 1/4 pi. In this case, my r is 60 squared. And I get, this one is 1/18 pi centimeters per minute. All right. If we were to go back and do a simpler one, say, assume that x and y are both differentiable functions of t, find the required values of dy dt and dx dt. Well, if y is the square root of x, then first of all, let me do dy dt. dy dt is going to be equal to, let's see, this is going to be 1/2 x to the minus 1/2 times dx dt. So if I'm looking for dy dt when x is 4 and dx dt is 3, this is going to be 1/2 x is 4 to the minus 1/2 times dx dt, which is 3. All right, so this is going to be 3 divided by 2 square root of 4, which is 3 divided by 2 times 2, which is 3/4. For part B, I need dx dt when x is 25 and dy dt is 2. So I'm going to solve this right here for dx dt. So dx dt is 2 dy dt times the square root of x. So this is going to be 2, dy dt is 2, and the square root of x is 25. So this is 2 times 2 is 4, times 5 is 20. Now there are some things you just simply have to know for this unit. You have to know the circumference of a circle, area of a circle, rectangles, triangles, and for a right triangle, make sure you identify, I guess this is your hypotenuse. That's kind of misleading here. So if this is your hypotenuse, and this is your y, and this is your x, h squared is x squared plus y squared, while for any given triangle, the area is going to be 1/2 base times height. For a parallelogram, of course, the area is the perimeter is 2a plus b, and the area is base times height over 2. Now, for volumes, for a rectangular solid, for a sphere, for a cylinder, make sure you know those. All right, give this a go and see what you can do.